Hello, in this video we're talking about waves, Unit C. We're going to try to go over all of Unit C, at least the really, high level details, some of the big picture ideas. This is a gigantic unit. There's a lot to know, so you want to supplement this with lots of reading, studying, practicing, and so on, but we'll try to hit some of the biggest ideas. So here we go. The first topic is simple harmonic motion. C.1 is where you find this stuff. One thing to keep in mind, simple harmonic motion is not a wave. It's like a thing moving up and down or side to side. So these can like cause waves. An oscillation can cause a wave. But that's going to be one thing to keep in mind of like when you're doing wave stuff and when you're doing particle stuff. This is particle stuff. The definition of simple harmonic motion is this graph and this equation, this first equation. Remember, the deal is if your acceleration is proportional to displacement and towards equilibrium, in other words, if A is always in the opposite direction as X, then you got yourself some simple harmonic motion. Calculus fans, you can think about why, if you know a little calculus now. You need something where the acceleration is proportional to X, but negative. And we know maybe acceleration is like the second derivative of displacement. So can you think of any math function where if you took the derivative twice, you would get at the same kind of function with some stuff in front and a negative sign? Sounds like sine cosine stuff to me. So that's kind of why, but you don't need to know any calculus for IB physics. Just know that's the definition. And this graph is the one you want to be thinking about to define SHM. You got some equations for masses on springs and pendulums. Only use those for those situations. If something has a length and it's oscillating, like that doesn't mean you use this. Only use this if it's a pendulum. Only use this if it's like a mass on a spring. Yeah, but you can find like the period of those things. And pretty commonly you combine that with the second equation for period in terms of frequency and angular frequency. Like if you need to know the angular frequency of a spring mass oscillator, you could maybe see that as square root of K over M. So a lot of times you're combining these equations for fun stuff. Speaking of fun equations, HL, you got a whole bunch of equations here. And this is where you really want to think about what these are for. These are for a particle on a wave, is a good way to think of it. Or again, something just like a mass on a spring. So if you're talking about one particle on a wave and you want to know where it's at or how fast it's going or what its like potential energy is at some distance, that's what these equations are for. These equations have nothing to do with waves. Again, it's like a particle on a wave or a mass on a spring, something like that. If you're dealing with waves, you're talking about this kind of thing. Many, 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 many particles all doing oscillations. All right, so those like C.1 simple harmonic motion equations would be great if you wanted to pick one of these dots and like find its velocity at some point. Yeah, or find its displacement at some time. But if I want to talk about the overall wave, we got some other ways to do that. All right, here's some definitions. You want to know a wave doesn't transport matter, it transports energy. Watch any one of these little dots. They're not really moving anywhere. They're just going side to side or up and down. Yeah, like watch the little red ones in the top one. It's fun. Your brain is being fooled. They're not moving left to right, really. They go back and forth. Okay, so those are our two types of waves. You could have a longitudinal wave as the long ways wave, or a transverse wave. It's all about which way the particles are moving relative to the wave itself, which is like which way is the energy going. In both of these, that's left to right. Sound is the wave to think about for a longitudinal wave. And most other waves you're used to are transverse. Like light is a transverse wave. A wave on a string is like a transverse wave. Wave in a stadium is a transverse wave, Okay, light is a good one to know about. Light we often model as a wave, an electromagnetic wave, which is something fun like an electric field and magnetic field, oscillating in size and direction, perpendicular to each other. And the rate, the frequency they go back and forth at tells you about like the color of the light. So remember, you got your EM spectrum in the front of the data booklet, which is very handy for lots of different units and stuff. So make sure you know the general regions there and kind of what the deal is with them. Okay, those are your types of waves. If you're doing some wave math, you are often using this equation, the wave equation, where it's the whole wave speed, frequency, wavelength thing. Yeah, so remember frequency is hertz. A hertz is a cycle per second. And it's good to think about the whole frequency wavelength thing because they're inversely related, we could say. So picturing especially like red light versus blue light is a good way to do it. That's a common kind of problem. They'll ask you about like red light is doing something versus blue light is doing something. And you're like comparing what's going on. And it's usually going to come down to the fact that since those two waves travel at the same speed, the speed of light, the red light is on like the long wavelength side of the spectrum. And because it's got a longer wavelength and is traveling at the same speed, the frequency is lower. Count like how often a peak is passing, over here, compared to the blue light, which is close together, short wavelength. It's got a high frequency, more peaks every second. Okay, so thinking about the frequency wavelength thing is a good way to understand, those like core pieces of a wave. Okay, there's lots of other wave terms, and some of these can be quite confusing because they sound so similar. First up, diffraction. Remember what diffraction is? Diffraction is if a wave goes through an opening, it will spread out. Or around a barrier, it will spread out. You get the most diffraction when the size of the wave is about the same as the size of the opening. By size of wave, I mean the wavelength, the distance between the peaks of the wave, or like distance between compressions or something for a sound wave. Yeah, so you get that the most when it's like the same as the size of the opening. Which like for light means you're not going to see light diffract through a doorway, but if you get a little tiny slit, it will diffract. Okay, a totally different thing is refraction. And that's the bending of a wave, almost always light, when it moves from one medium to another. Also, there's reflection. So diffraction, refraction, reflection. Make sure you know the difference. They're all completely different things. Refraction and reflection are like what comes up in the Snell's law situation where, our classic kind of thing where there's light going from like air into glass. Part of the light maybe will bounce off. That's the reflected piece. This rule's easy. The angle of incidence equals the angle of reflection. The bit of light that goes through the glass is more fun. In this case, it would slow down, which means it bends inwards towards the normal is a good rule to know if it slows down. So it bends because it slows down. Also, you want to know how we measure all of these angles, which is relative to the normal line. This kind of line, normal means perpendicular, perpendicular to the boundary. So don't measure from like the horizontal, which you'll be tempted to do sometimes. These all are relative to the normal. And one other fun little, there's our Snell's law from the data booklet. One other fun Snell's law thing is the whole critical angle situation, which is super specific, but is a good one that comes up pretty often. This is used in like fiber optic cables is one of the big examples. Okay, this is only happens if you have a wave going from a high to low refractive index, because in that case, the wave bends away from the normal line, right? If you slow down, if you go into a denser medium, we say, go from a low to high refractive index, the wave slows down and bends inwards. But if you say have light going from glass into air, then the light speeds up when it gets to the air, which means it bends like away. So in this case, you could have a refraction angle so big that it's 90 degrees, which would mean you don't refract at all. We call that total internal reflection. The critical angle is the angle that makes that happen. So what it is the critical angle is the angle of incidence when the angle of refraction equals 90. So critical angle is theta 1 when theta 2 equals 90. That's what it is. That's how you want to set up that problem. So see if you can picture why that all kind of happens. And if you're above this angle, you have total internal reflection. Nothing refracts. And it all stays like in your fiber optic cable or whatever. Okay, so diffraction, refraction, reflection. Know the difference. Know how to do the critical angle thing. Also, one other fun thing to know that's not in the data booklet, I don't know why, is intensity. This isn't really in there. There's one like apparent brightness equation that's pretty good that shows you like the whole inverse square law situation. But you want to know the definition of intensity, that it's power over area, like from a wave. So power over area, it's a watts per square meter thing, is how you want to think of intensity. So that comes up sometimes, and you want to know in general what it means. Okay, interference is a big wave topic. The whole idea with this is waves meeting at a point. When two waves meet at a point, the rule officially is that their displacements add together, which is called superposition. It really is just the math sum of the two waves. Get two different like sine, cosine waves happening in Desmos, add them up. Hey, you just did some superposition. So when two waves meet, that's what they do. Their displacements add together. So if they meet and one of them's got like a big positive displacement and one of them's got a big like negative displacement, they'll cancel each other out. If they both have a big positive displacement, they'll add up. If they both have a big negative displacement, they'll add up. So in other words, we say if the waves arrive in phase, you have constructive interference. And if they arrive out of phase, you have destructive interference. That all comes down to path difference. Path difference means subtract the distance like that each wave has traveled to that point. If that difference is one wavelength or two wavelengths or 15 wavelengths, you're going to have some constructive interference because the waves will line up nicely again. Like here, top wave has gone 1, 2, 3, 4.5 wavelengths to get to this point. Bottom wave has gone 1, 2, 3, 4, 5.5 wavelengths to get to that point. The path difference is one wavelength. This one went one wavelength further than the other one, which, if we can picture that, means they meet lined back up again. But in this one of them went like half a wavelength extra, which means they arrive out of phase. You got a peak and a trough meeting here, they'll cancel out. So if the path difference is like a wavelength and a half, or half a wavelength, or 19.5 wavelengths, the two waves meet out of phase, they cancel out. Okay, this stuff is kind of complicated, so take your time studying it. But we often have the two source interference pattern that looks like this, where I got two different sources of waves, like I'm making two waves in a pond or something, or it's two speakers making sound waves, or two slits making light. There's going to be places where the waves meet up crest to crest and trough to trough. Those will be points of constructive interference. There'll be points where they meet crest to trough and trough to crest, and those will be destructive interference points. Yeah, and so again, it's all about the path difference. If you can find a spot where you're two wavelengths away from the one wave and three wavelengths away from the other wave, they're both at a maximum, that'll be constructive interference over there. Okay, so you get this kind of overall pattern. We have an equation for it, which we'll look at in a second. So study the interference stuff best you can. It's kind of tricky, but it really comes up a lot, and it's good to know in as much detail as you can. Here's a little more detail. If you have that two source interference pattern, if you got two speakers making noise, you got loud spots, quiet spots, loud spot, quiet spots, the intensity of those points would look like this: loud, quiet, loud, quiet, loud, quiet. Or water wavy still, water wavy still. Or kind of sort of bright, dark, bright, dark, bright, dark. That one's a little more exciting, but same idea. Well, we have an equation for two source interference. This equation is for two source interference. You want to use this equation if you have a double slit or two speakers or something like that. This equation is a little tricky because all of these things are like distances in meters. You want to know what's what. S is how far apart the maxima are, which is also how far apart the minima are. So sometimes they're tricky and they ask you for the distance between a maximum and a minimum. So you take half of that number. But S, I think of as spacing, if that helps at all, the space between the bright spots. Lambda is always the wavelength of our wave. Big D is the distance to the screen, we sometimes say, because we're often talking about light here, like projecting a double slit pattern onto a screen. But it could be like you're walking along a line with two speakers nearby. Little d is the distance between the sources of the wave. So the distance between your slits, the distance between your speakers, that kind of thing. All right, so know what's what in this equation. If it's two-source interference, use this. Before we look at the double slit, there's an extra little detail that happens there because when light goes through a slit, it does a fun thing, diffraction. For spooky reasons, even if it just got one slit, one kind of source, when light passes through it, it decides that it's going to find little spots where it cancels itself out and find spots where it makes itself extra bright. Ideally, you do know the whole Huygens principle thing, this idea of infinity little tiny wavelets all making their own little baby waves that sometimes meet up in phase and sometimes meet up out of phase. But long story short, light goes through a slit, you get this pattern. You get a really bright central bright spot and then like much dimmer secondary maximums over here. Get the kind of octopus shape if you graph the intensity along the distance of the screen. Bright, dark, bright, dark, bright, dark. Everybody wants to know the pattern. HL students, you also have an equation for it. Like lots of things in the data booklet, there's not a lot of context here. You have to know this is the equation for single slit diffraction. That's the only thing you use this equation for, and that's the only equation you got a chance of doing anything with if it's a single slit problem. You also have to know the super specific detail that theta is the angle to the first diffraction minimum. It's the angle from like looking dead on at the screen to you look a little bit to the side to that first dark spot. That's the angle. They like to do stuff where they say like, so find the width of the bright spot on the screen, which is now just a trig problem. If you know this angle, you could find the length of this leg of the triangle and then say double it to get the width of your bright spot. Yeah, but that's your single slit equation. Okay, so the double slit experiment is super fun. Young's double slit where you shine light through two slits because two things are happening. You got two sources of waves. They're going to interfere in a two-source interference situation, but also light is passing through a slit, so it's also going to do the diffraction thing, and both of those patterns happen together, and it's a superposition situation. So they add up. They have often asked you to draw this graph before, this whole crazy graph of like a pattern inside of a pattern. It's the whole max min, even size max min from two source interference inside of the single slit octopus shape, the single slit envelope, we call it sometimes. All right, you want to know which of these are two source interference maximums and which one of these are the single slit maximums. The overall patterns, the single slit, the inside patterns, the double slit. So you could say like the closer together peaks, the distance from like this peak to this peak, kind of this way would be S in the double slit two source interference equation. Whereas the angle to this first overall dark spot would be your theta in the single slit equation. So you can use both equations on this pattern, which they will ask you to do. And here's another picture of it, the two source thing. And again, this is usually for double slit is where you see this the most. You got your two slits. You do want to ideally know the whole where the path difference comes from here, that the path difference is d sine theta. But more or less, they meet at different points. And that's what it kind of looks like. D is your distance between the slits. Big D is how far away the screen is. S is your like distance between the maxima. Okay, HL, why stop at two slits? Why not do three slits, four slits, 16,000 slits? That's a diffraction grating when you have lots and lots and lots of slits. The pattern looks like this. You want to know the pattern a little bit. You want to know we name these different sections the diffraction order of n. And this equation right under the single slit equation is the equation for a diffraction grating. You can kind of use this equation for double slit too, but usually you use this for diffraction grating and the other one for double slit. So think about how this works a little bit. N equals 0 is like, this is assuming we have a white light coming into your diffraction grating, which remember has all the colors of light inside of it. If n equals 0, you have no diffraction angle, so all the light just kind of makes a bright spot here. So diffraction grating, white light gives you like a bright white spot in the middle. But then the bent parts are exciting because the angle of diffraction depends on the wavelength. And so the longer wavelength light pieces get diffracted at a bigger angle, so the red light gets spread out more than the blue light, and you get the rainbow color here. And you have these different orders. So you'll see that at one time for n equals 1. You'll see that again further away for n equals 2. Common problem here is they ask you how many bright spots can you see. What you do there is set theta to 90, because like the furthest you could go is 90 degrees. You can't diffract more than 90 degrees or you're not going through the slits. So if they say how many bright spots, set theta to 90, solve for n, and then draw it. Think about it. If the maximum n when theta equals 90 is like 3.9, how many bright spots do you see? I would say you see 7 bright spots. You can't see the fourth one. If you can math, see up to 3.9. You can't see the fourth one. There's not actually a 3.9. That's just a math thing. That means you can see the third one, but not the fourth one. You can see n equals 1, n equals 2, n equals 3. There's a set of those on either side, and also the one in the middle would make like 7 total. That's a common diffraction grading problem. Added to the list of stuff to practice. Let's keep going. Standing waves. Standing waves is a whole topic that is not in the data booklet at all, because they expect you to know lots of stuff about standing waves and kind of be able to derive some equations. Here's what a standing wave looks like. Make sure you know the rules about standing waves and how they're different from traveling waves. Also know how they get formed, which is like by 2 identical waves passing through each other in opposite directions. A standing wave has nodes, points on the wave that don't move at all, and antinodes, points on the wave that move like the most. That's super different than a regular traveling wave, because all of the points in a regular wave like all have the same amplitude. They all go up all the way and down all the way eventually. And they're all like out of phase with their neighbors. Not a standing wave. You got nodes that don't move, antinodes that move. And all the points like in between 2 nodes, say, are completely in phase. They all hit a maximum together. They all hit a minimum together. They all go through 0 together. Yeah. So know all these differences. There's what a wavelength looks like on a standing wave. And here's how these equations work. You need to be able to come up with these equations or memorize them. They kind of expect you to be able to come up with them by knowing the boundary conditions, like the rules about what happens at a open end of a pipe versus a closed end of a pipe versus a fixed end of a string. So here's the situations. String fixed at both ends is a common one. You got yourself a guitar, you got yourself a standing wave, a string fixed at both ends. And the first, what we always do with these is we find the first harmonic. The first harmonic is the simplest shape you can set up with those boundary conditions. So if I got a string fixed at both ends, these ends have to be nodes because it's like fixed, so they can't move. So if I have 2 nodes, I would need an antinode in between. That's like the simplest standing wave I could put on here. And if you can picture it, that's half of a wavelength. In other words, the wavelength of the wave is double the length of the string. Turns out the same thing happens if you have a pipe open at both ends, just like the inverse, because the rule for a pipe is the open end is always an antinode. If I have an antinode at each open end, I need a node in between. That's also half a wavelength. So in either case, the length of the thing is half a wavelength. In other words, the wavelength is 2L. If I put wavelength equals 2L in this equation, I get this. I solve for F. That's my fundamental frequency. The frequency of the first harmonic, which depends on the speed of the wave, which is usually speed of sound if we're talking about like a pipe. L is the length of the thing. Okay, so be able to draw all of that or memorize that that's the one for those 2 situations. And you have a different situation if you have a pipe closed at one end and open at the other, because the boundary condition for the closed end of a pipe is it has to be a node. Remember we're talking about sound waves here, which go side to side. If the pipe is closed, it has to be a node because the air can't go side to side. So that's a node. The open end is an antinode. That's a simple wave. All we got to do is connect the node to the antinode. We got a quarter of a wavelength here instead of half a wavelength. And so the wavelength is 4 times L. Put that in times frequency. Solve for frequency. It's half as big as the other fundamental frequency. Okay, so you need to be able to draw those shapes and come up with these 2 equations for the situation. or memorize that those are the situation. Also, memorize what the harmonic number means. It means this: the nth harmonic is n times fundamental frequency. So if we say like the third harmonic, you triple the fundamental frequency. That's the frequency of the third harmonic. That's what they kind of mean. See if you can sketch this out and see why it's true, but there are no even numbered harmonics for a pipe closed at one end. They don't fit. If you try to draw on here a standing wave that's double the frequency of this one, it won't work because you won't have like your nodes and antinodes in the right place. You'll only have like n equals 1, 3, 5, 119, whatever for a pipe like this. Okay, study standing waves. There are a lot, but there you go. Last thing, the Doppler effect. The Doppler effect, picture this picture. Picture your everyday life. Hearing the ambulance whiz by you on the road. You know what it sounds like. You want to know that while a thing is approaching you, the wave fronts get bunched close together, so you see short wavelength, here a high frequency. If the thing's moving away from you, the opposite, the waves are more spread out. Long wavelength, low frequency. Do you remember these things? So if we're talking sound here, these things all travel at the speed of sound. The speed of the wave is not different. The ambulance doesn't make the sound wave go any faster or slower. That's just about the air. But because the ambulance is moving, when it emits the waves, the wave fronts get scrunched up or spread out. So the speed of the wave does not change. That's like a common thing they're going to try to trick you with. Okay, everybody, you have an equation for the Doppler effect for light. Remember, light does this too. You can have like red shift, blue shift, based on whether things moving towards you or away from you. Make sure you know which way is which. The F and the regular lambda are like the at-rest numbers. If you're in a lab, usually is how they say it. Like, what's the frequency? What's the wavelength of this hydrogen spectral line in the lab? What's the wavelength when you look at a galaxy moving away from you? Oh, they're different. How fast is that galaxy moving? You can figure it out. HL people, you also get these fun equations for the Doppler effect for sound. Typically, you can kind of do other waves with this, but it's almost always sound. And okay, remember the deal with this. This is the tricky thing. The plus minus is not like uncertainty. It means you have to pick, and you need to use your physics brain and think about which one of these should you add or subtract based on the situation. So picture it. It is my sincere hope that as you're taking the IB exam, you're sitting there muttering to yourself, making noises and going like, which way is it working, right? So like if the source is moving towards you and you got to find the frequency, you know F prime should be bigger than F. It's a higher pitch when it comes towards you. And so to make that work, should I add or subtract here? Well, it's in the bottom. I think I should subtract. If I want to make F prime bigger than F, this should be a minus sign, which tells me what to do when it's coming towards me versus going away from me. That's one I don't recommend memorizing because it's in the opposite side of the fraction in the moving observer case. So you got like 4 rules to memorize. It's confusing. This is a much better one to think concept-wise about. Should F prime be bigger than F or not? And choose plus or minus to make that work out. Yeah. Only other Doppler thing to remember is this has nothing to do with volume. Volume and pitch are completely different. Pitch is the tone, the note, right? Volume is how loud it is, which may change too if something's moving close to you versus far away from you, but that's got nothing to do with Doppler effect. So try not to confuse this with like volume or intensity. This is just about the note, the pitch that you hear, or the wavelength, the color of like light for a light one. Okay, there you go. Lots of wave goodness for you. So hopefully this helps get you started and jog your memory on all the different waves fun we've had. So again, lots to kind of dig into and review more here. So decide what you want to tackle, try some practice, and have fun.